So basically what this section's starting, and that's why the 4.8 with antiderivatives, is we're going to say that we have a function and we want to find the area, say from here to here, underneath that graph. That's the whole shebang, and that's what you're going to basically be doing in Cal 2. I mean, you'll get more difficult stuff as well. Well, one way to do this is you could take rectangles and make rectangles under the graph. Of course, they're not going to be perfect, so you even go to here. And we know how to take the area of rectangles. And I'm going to show you that here in a minute. And so that's the first way you learn how to do this, is you do a whole bunch of rectangles underneath here, and you get the height times the width. You add up all the areas. I think it's kind of silly to make you guys go through that. It's a good exercise for those of you that have never seen this before, but I think it's kind of silly to make you go through that because you did area of rectangles in what, 3rd grade or something? Yeah. Okay, so, and you'll get to see this, but I want you to keep thinking. It's like the first of this class. I said derivatives, slopes, slopes. Now we're getting into what's called integration, area. Okay, so that's where we're going with this. All right, so this is the idea behind the integral, is we want to compute area, volumes, and we'll even see. This is something, if any of you have ever taken statistics and you have this, pretend that was a normal bell-shaped curve, and you have this bell-shaped curve, and in statistics you have to find probabilities in here, and you look them up in a table. When I took statistics, I actually had to find that area, meaning I had to integrate the actual function, and so it was a little bit more trouble. But if you haven't taken it, or you're going to later, or you have, all those numbers in those tables are coming from finding areas underneath the bell-shaped curve. Okay, so you're still doing this. All right, so this is kind of what I've been saying, is that we want to break our quantities into small pieces. Once again, I just think the easiest way to see this is with pictures. And basically what we're doing here is the smaller and smaller pieces are rectangles, okay? And we want to get their width smaller and smaller and smaller, and the number of rectangles gets larger and larger and larger because we would get a better approximation. So basically we're going to end up, this is where we're going to end up with the easier way to do this, is say, well, let the number of rectangles go to infinity. Let their widths basically get to 0, and this whole, take the limit of these sums, and this whole thing becomes an integral. So if I wanted to find the area underneath this function here, so underneath this curve, one way, and it's, it's one of these things, I'm sure this guy did it first, and then somebody else said, oh, there's an easier way. But one way you could do it is by drawing rectangles. So what I've done here is I've put 2 rectangles here. The width you can see is 1/2. You can find heights of any function because you just plug in this value into your function. So that's where we get these numbers. And then the area of those 2 rectangles by taking the height times the width, the height times the width. And that would give me an approximation. Well, hopefully you're looking at that saying, well, it's not a very good one because all this junk out here is getting accounted for, so we have extra area. Certainly, your estimate is going to be greater than the true area of what's called an upper sum. Now, sometimes, and you'll even hear me say this, you can call these left-hand sums, but the only problem with that is a left-hand sum won't always be an upper sum. If this function was increasing, and you'll see this here in a minute, if this function was increasing, it would actually be below the function, a lower sum. So I wouldn't really get into the habit of saying, and what do I mean by left hand? I'm on the left hand of that rectangle there, okay? And so I could get a better approximation. How would I get a better approximation? Make this width smaller. In other words, I end up with more rectangles here. And so then I get each one of these areas, and this is why I said we're not really going to go. It's a good exercise to go through when you're first learning this. But all I'm doing is I'm taking, if you notice, the width of each one of these is 1/4. So I'm taking the height times the width, the height times the width. So you can see the width is 1/4 on each one. And then I sum up all of those areas, and that gives me a better approximation. But again, this is still larger than my actual area. A lower sum is I'm below the function. If the function is decreasing, I tend to call that a right hand, okay? So that's the right-hand side of my rectangles, but it's probably better to think of it, it's below the function. And so as you can see here, the problem is this blue area is not getting accounted for. This one looks kind of weird, but if I'm at the right-hand side, and so how I draw these, and we'll do one of these in a minute because you have them in your homework, is I start on the right-hand side and I move left and I do my rectangle. Right-hand side, move left, do my rectangle. Right-hand side, move left, do my rectangle. Right-hand side, there's no place to go down. So actually, this rectangle here would have an area of 0, okay, because the height would be 0. The width would still be, you know, the width of this 0.25, but I wouldn't be getting any of this area. So as you can see by looking at the lower sum and the upper sum, the area is somewhere in between here, okay? Now, if you think about this, and most students do, a good way you could get a better approximation is most students say average, okay? Average the values. Or you could actually take the midpoint, which we'll do that as well. But again, all of this depends on how much error that you care about. In this case, this error can't be any greater than this. If I subtract these two values to be able to see how much error I get, and so if you're doing something that's fine, then that error for you. Here's what I was just mentioning, the midpoints, kind of taking an average, so I go in the middle, I cut this width in half, go up in the middle and draw my rectangles, same thing here, and it looks like this overshot kind of takes that missing. This takes that missing, this takes that missing, this takes that missing. It's not an exact science because that's still an approximation. It's not exact. It's because there's going to be, and you can kind of see by this one, there's going to be areas that don't, wipe out completely. All right, so these intervals that you see me setting up here, you can find them by whatever your interval is of your function. So if I have this function, and my interval is from A to B. And once again, what am I trying to do? I'm trying to find this area underneath the curve. Then I can, depending on how many subintervals I want, rectangles, okay? If this is, say, from 1 to 5, and I want every one, let's say this is time, every 1 hour I want to check this again, then I simply would plug in to this formula. I would plug in my interval, my 5 minus 1, and then in this case, if I wanted 4 rectangles, then I'd put my n equals 4. So this value is however many subintervals you want. And you're going to see I think rectangles all the time, but there is going to be a point where this is flat and we're just looking at one dimension. So it's not going to have an actual. And so then we evaluate at different points in this subinterval. So all of these things here, again, if I redo these slides one day, I'll probably put pictures because I think it helps with pictures. All this says here is I have this interval, and within here in my subintervals, I'm picking points that I'm going to evaluate my function, my height times width, and I would call these, if this is somewhere in this first subinterval, and it doesn't have to be an endpoint, it could be within that interval, I would call that first one C sub 1, the second one C sub 2, C sub 3, and so on. So in other words, that's where I'm going to evaluate the function. Now hopefully you're thinking, well, where would I know, you said do left side, do right side, do midpoint, where would I know where to put that point? At the end of the day, you're going to see it doesn't matter, because what we're going to ultimately do is take this subinterval and shrink it to 0. I mean, that's eventually what we want to do. So we're not sitting here drawing these rectangles and I say, well, can you get something better? Well, certainly if I make the rectangles smaller, I can get a better approximation. Well, can you even do better? Make them smaller, smaller, smaller. Basically make those widths of the rectangles go to 0. And so this is my sum here of taking the value of the function at those points times the width. Remember, this is going to be the width of my interval. So in other words, this is the height of the function times the width. So that, again, would be the area of my rectangle. I go to the height and then times the width, and then this is my next subinterval, and I just keep going. Usually, these are all the same, usually. Again, they don't have to be, because if this is the width of my interval, and eventually I'm going to shrink that to 0, then it doesn't matter what this value is. What I'll do is I'll pick the largest one and start shrinking it, and then the others will shrink with it. But it is nice to make, in other words, all of your rectangles this same width here, the change in x, because you can see it makes it easy to write one formula. All right, so how do you get a better approximation? Easiest answer is more rectangles. Not just more rectangles, but making this width smaller. So in other words, I keep shrinking and shrinking and shrinking this width. As you can see, my error here is getting smaller and smaller and smaller. Of course, this being a lower sum, this being an upper sum. And so I get these values. I could even do a midpoint as well. And I could do this in a table where, notice I started with 2 rectangles, and I'm going to tell you that's the exact area. We'll see why coming up. But so I just that's the answer. So if you look at the 2 rectangle one, these are pretty bad approximations. You know, the midpoint's not that bad. But as I add rectangles and as I shrink their width, then you can see I'm getting closer and closer to the true value. Well, as I let the width go to 0, as I let the number of rectangles go to infinity, your mind should pop up and go, oh God, limits again. That's what this is. Basically, that's what we're going to get to, and that's why I said I don't really have you guys do much with drawing rectangles, because there's an easier way, and it's a more accurate way. All right, so suppose we know our velocity function. So this is where I know it's been a while, but when we did 4.8, we said we knew the velocity, we wanted position, and that's when we started doing antiderivatives. So this car's moving down a highway without a change. I want to know how far it traveled between these 2 times. Well, if you remember, if this is my velocity and I find its antiderivative is the position function. It's antiderivative, and this is known, then all I have to do with the antiderivatives is evaluate it at those 2 times. So that's pretty easy to do. So I find the car's position based off of my velocity, my antiderivative, and so I get my function, and then I plug in those various times. And this is important because you're going to see this again, where I'm just subtracting, I'm evaluating the function at the later time minus the starting time. Well, let's say the antiderivative is not known. Then what do? Well, we draw rectangles, basically. And so we approximate this with a sum, and we would subdivide our interval into short time intervals. And we're going to consider velocity being constant, which you know the formula, distance equals velocity times time. And then we want to approximate this distance on these different subintervals. So again, this one you kind of don't really think of rectangles because there's no height to it. Okay, we just have our line here of our time, and this is our change in time. And I made these equal. Again, they don't have to be, and you'll see, later why they don't have to be. But so within here, this is on the slides before, you saw that C sub 1, C sub 2. We're just calling it T because it's time. So I pick a value within this subinterval, a time. In other words, I could be sitting there with a stopwatch, and checking the velocity at this time, checking it this. I continue to do this. Well, again, I can get my distance across here because I know my formula. So I get a second value, I get a third value, and so on, and I continue to do this until I want to stop. And then this, once again, is just telling me this is velocity times time. That's your distance. I'm doing it for the next subinterval, doing it for the next subinterval. So all I'm doing is I'm summing up a bunch of these distances to get the total distance. All right, so let's do it with an actual function, so it probably makes a little bit more sense. So here's a velocity function of a projectile fired straight into the air. If I want to estimate how far the projectile rises during the first 3 seconds. And I'm going to give you the exact answer. Okay, so the exact value is 435.9. If your function is decreasing, then if I choose left endpoints, this gives an upper sum. This is what we saw. If I choose right endpoints, I get a lower sum. So if I choose left endpoints, that means I start at the first value, and I choose values to the left. And so I just evaluate my function. Now you could say there are rectangles. In this case, you could say there are rectangles here, but we really don't think that way, saying that we're just doing distance here, that there's any height to it. And so what I'm basically doing is evaluating the function at each one of these left endpoint values times the width. Well, it just so happens that, and you could write this, if your width wasn't 1, you would need to multiply it times the width, okay? But each one of these are 1, so no need to do that. Then I take, this is what I did on the other, I'm taking the distances of each one, and I add them all up. I sum them. I didn't notice I did that. This is in the next section. That's just the sigma. I think most of y'all know that. But that just means to sum all of those values. And as you can see, it's a little more. Okay? Again, depends on how much accuracy you want. Well, if I did the right endpoints, that means I start at the right hand of each subinterval. Those values in, and I get another estimate, which again is not exact, but it's close. So how could I get a better approximation? Because I know the actual value that I want here. I could get a better approximation by having more subintervals. And certainly, instead of using the length 1 of my subintervals, make them smaller, smaller, and smaller. So once again, where are we going with this? My number of subintervals is going to infinity, and then my length is going to 0. Or my width, I should say. The length of each subintervals are the actual width of it. And so as you can see, we get better and better and closer to our exact value. All right, there is absolutely nothing on there that you will be, it's hard to say you won't be tested over that because you need the knowledge for later sections.